day, and welcome to the Division of Education, Innovation and Energy's e-learning program. I am Mr. Atwell. I know we're not dealing with mathematics today. Today we're actually looking at physics. Yeah? So we know that the time is short, and I'm sorry that we can't go into, a full content detail about every little bit of the information, but we're trying to do a crash course so that at least you'll have some information so that whenever the question do show up, you'll be able to answer correctly. So let's look at section E of the syllabus, which is the physics of the atom. This is the fun part of physics for some of us, and this is the part where some of us actually shy away from. But what we're going to do today, we're going to try and get through most of the fundamentals, and then on our next session, we'll actually go into the calculation part. So, what are the objectives for today? Today, we want to be able to understand and describe the different models of the atom, to understand the structure of simple atoms, and understand what is radioactivity. Just some simple fundamental basics today. Let's go one time, no sticking. So we want to go to the first model of the atom, right, which was from Dalton, 1803, and even backwards, where he was saying, well, the atom is just like a pool ball. So, you know that particle and matter is made up of atoms, and the atom is just this one, like a ball. It's just there, and it just exists, and then all the balls are connected, and that's what makes it. Well, that was existing for some time, and of course, people had this idea, okay, well, a spherical shape for an atom, and whatnot. But then, Thomson was like, wait, that's an electron. So Thomson actually discovered the electron and realized that the atom must have electrons. But it can't just have electrons, because if it has a charge, there must be something holding the charge together. Yeah? So he realized that, he hypothesized, I should say, not realized, but hypothesized, that an atom actually has fixed negative charges, and then just this positive cloud around it, keeping the negative charges together. It sounds weird to us, right? Because we know what an atom's supposed to be. But this was his model in 1897. Now, he called it, and it was called the plum pudding model. Now, we don't really know what a plum pudding is across here, right? But what we know about sweet bread. Yeah? We don't know about plum pudding, we know about sweet bread. But it's the same basic thing, right? Basically, it was like the atom was like a loaf, yeah? Where the raisins in your sweet bread would be like your electrons. Yeah? So his model was your electrons were fixed, and then your whole dough, all your dough and your sweet bread and thing, all the sugar you like on the top, that was your positive charge. So your positive charge was distributed across your whole atom, and the negative charges were fixed right where they were. But people didn't really believe it, because he was like, oh, that ain't making so much sense, whatever. But he did discover the electrons, so they was like, all right, cool, we'll at least entertain your idea for a bit. Some of them. Others were like, psh, that's rubbish. But moving forward, we'll talk about the Rutherford model. Now, it's called the Rutherford model, but the people that actually did the experiment was Geiger and Marsden, right? So it's called the Geiger-Marsden experiment, and then Rutherford, brought it before the science people at the time. So based on the Thomson model, what he did is that here, there was what we call alpha particle radiation. We will get to that in our time. But what you need to know is that these were, heavy particle radiation. They had a lot of mass. And it was shot at gold foil. Now, if Thomson's model was true, and the mass of the gold was so evenly distributed across, then the particles would just go straight through as though, they wasn't being affected by anything per se. However, when they did the experiment, what they observed, yes, they did observe that a lot of the rays did go straight through, about 98%, some people may say. A lot of the rays went straight through, but what they did realize, however, is that some of the rays, like this one, were partially deflected. And even fewer were deflected by angles greater than 90 degrees. So what is this saying? This was saying that Rutherford's model was nonsense. Talking straight. that Thomson's model was nonsense. That Thomson's model says, well, if this experiment was to work based on Thomson's model, everything would just go straight through. But however, Rutherford and Geiger and Marsden showed that there was heavy deflections by more than 90 degrees, which meant that whatever it was interacting with, whatever the alpha particles, remember, they are actually like heavy, right? They are like the heaviest radiation particles. So whatever the alpha particles were hitting was actually dense enough and strong enough, positively charged, strong enough to reflect it away. Yeah? Imagine you have a friend and you're running to your friend. Now, if you're bigger than your friend and you're running to them, you will run them over. Yeah? But if you were trying to run into me, now I'm a pretty huge guy. Yeah? I'm like 6'5", probably like 320 pounds. If you were to run into me, it might be like running into a brick wall for some of you. Yeah? And you might actually go back. In fact, yeah. So this is exactly what they realized. Because whatever it had hit had to be dense enough and positively charged enough to deflect the alpha particles almost all the way back 180 degrees. So then this came up with a new model of the atom, where there was this positive region, which he called the nucleus, and it was surrounded by electrons on the outside. So the electrons were moving on the outside, and then there was a positive region. Now he brought this model, and the scientists at the time was like, that's rubbish, because it don't explain certain things. If the electrons are moving, where's the energy for the electrons coming from? And if the energy from the electrons is coming from the atom, then how is the atom not losing energy? Or energy cannot be created or destroyed but converted from one form to the next. If there's a positive region here, what's keeping the positive charges together? Because we know that like charges repel and unlike charges attract. So if all the positive charges are in a very small area, why don't they just split up? Nonsense. And that is what they were believing, right? So, building on the Rutherford model, we had Bohr. And Bohr discovered that the electrons weren't just all randomly located, but they were existing on what we call electron shells at very specific energy levels, and that they were kept in orbit based on the electrostatic force of attraction between the electron and the nucleus, and also because of the centripetal force, and that will create the centripetal force to keep it in orbit. So Bohr came and changed the model of the atom so that Rutherford was basically, well, we have a positive charge and somewhere around we have electrons moving around it. Bohr said, well, yeah, I agree that can have a positive charge there, but these electrons aren't just moving anywhere, they're moving on very specific or at very specific energy levels. Yeah? Chadwick comes along after all of them and is like, wait, what is the thing that will keep this positive charge inside the nucleus by itself? So Chadwick actually discovered what we call the neutron. And he realized that the neutron was located in the nucleus, and that will provide enough of a mass to basically stabilize the positive charges and stop them from just repelling from each other and breaking up the nucleus apart. So when we combine all of them together, we have what we generally classify at this level as the modern model of the atom, where we have a positive nucleus which contains protons and neutrons with electrons orbiting on very specific shells or energy levels. Now, for those of you that did chemistry, you know about electron shells and how much should fit on a shell and all of that. But we're not focusing there, right? We just want to understand where we came to the model. So here we have a big breakdown. So we had Dalton first saying that the atom was, just had a whole idea of atoms, that matter must be made up of atoms. And these atoms are indivisible. And then they realized, well, the atoms can actually be divided into particles. So Thomson discovered that there were electrons, and if there were electrons, there must be some positive charge that's keeping the electrons from falling apart. So let's call it positive charge protons. And then Rutherford was like, well, there's a nucleus of protons and not just the protons all over the place. And then Bohr is like, well, yes, the electrons that are surrounding the nucleus are actually on electron shells. And then this guy, Schrödinger, was actually like where they're actually subshells to the shells, and they know there's this whole quantum aspect to it. And then Chadwick was like, hey, neutrons. That's what's holding the nucleus together. So basically, after all of that, what we need to know is that an atom is made of protons, neutrons, and electrons. There are also other particles, but we're not going to concern ourselves with that right now, where the protons and the neutrons are located in the nucleus, and the electrons are located outside the nucleus. So here's a cool word. I'll try it out one time. If a particle exists inside the nucleus, it can also be called a nucleon. Nucleon. So protons and neutrons are nucleons because they exist inside of the nucleus. Electrons are not nucleons because they do not exist inside of the nucleus. Simple, right? Nice. So let's compare them real quick. Electrons, we use an E, protons, we use a P, and neutrons, we use an N. Now, what's the relative charge? Hopefully you remember a little bit about charge. So electrons are negative, yeah? Protons are positive, and neutrons are neutral. So what is the actual value of the charge? Well, the charge on an electron is negative 1.6 by 10 to the minus 19 coulombs. And a proton is positive 1.6 by 10 to the minus 19 coulombs. So what you should also remember is that if we had one proton and one electron coming together, then the overall charge will be neutral. Because if we were to add these numbers, one positive and one negative, you realize that our answer is going to be 0. So the relative charge, electrons are considered to be negative 1 or 1 minus. Protons are considered to be positive 1 or 1 plus, and neutrons are considered 0. Now, what is the relative mass? Well, protons and neutrons generally have about the same mass, right? Where neutrons is just a little bit more. However, electrons are 1,840 times smaller in mass compared to the proton and the neutron. So here we have the actual values, right? Yeah? And in grams. So if it was in kilograms, this would be 9.11 by 10 to the minus 31 kilograms. This would be 1.67 by 10 to the minus 27 kilograms. What is key here is that this is in grams, right? Now, understand this. It means then, since the mass of the electron is way small, it means that the majority of the mass of an atom is located in the nucleus. Yeah? The majority of the mass of the atom is located in the nucleus, which is why when it comes to chemistry and talk about the relative atomic mass, we're actually talking about the mass of the nucleus. Yeah? Because the mass of the electron is almost negligible when it comes to the mass of the nucleus. Now, when it comes to an atom, we need to be able to represent various numbers on an atom. Now, in truth and in fact, there are 4 numbers, right? There are 4 regions. So if this is the element, X is the element, there is the number here, there is a number here, and more specific to chemistry, but sometimes we'll be using physics, are the numbers on those 2 sides. Yeah? So this number is called the mass number or the nucleon number. And because it's physics, that's represented by a capital A. Yeah? It is the number of protons and the number of neutrons. The number of protons and neutrons. Yeah? The atomic number, and of course, because it's atomic, you know what the symbol is? Z. Yeah? Is the number of protons. So if this number below is the number of protons, and this number on top is the number of protons and neutrons, it is simple for us to find the number of neutrons by simply subtracting the 2. So here we have that formula where the mass number is equal to the atomic number plus the neutron number. Yeah? So that if you ever want to find the neutron number, it will be the mass number, take away the atomic number. Now this number on top here represents a charge. Now if there is no number there, then the atom is neutral. And a neutral atom has equal number of protons and electrons. Yeah? A neutral atom has an equal number of protons and electrons. So if there is no number up there, all it means is that whatever your atomic number is, that's also your electron number. And this number refers to the number of atoms or molecules, number of atoms. So if there were 2 of the atoms, then this number will be 2. If there were 3 of the atoms, this number will be 3. But when it comes to physics, we don't really care about this one. We kind of care about this one, but we don't really use it much. But we do, so I'll leave it there. So the 3 that we really care about right now are these: BAP, BOP, and BIP. Yeah? Let's go. So, a little bit of notes. The atomic number defines the element. Which one is the atomic number? Is the atomic number A, B, or C? I shouldn't use A, B, and C. Let me change those letters. Is the atomic number going to be 1, 2, or 3? Where will the atomic number be located? At point 1, point 2, or point 3? It will be at point 1. Exactly. So whatever number goes in this position will define the element. No 2 elements have the same atomic number. And that's important to remember. Every element has its unique atomic number. The number of protons will define the element. And we actually arrange these elements in ascending order in what we call a periodic table. I'll show you a periodic table just in a bit. In fact, let me show you now. This is a periodic table. And we see up here that they represented the atomic numbers. They just have the atomic numbers represented here. They don't have the mass numbers or the actual mass or anything like that. So depending on the periodic table that you look at, you're going to see more information, less information. But basically, look at it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, going on, going forward, yada, yada, yada. But what do we realize? They're all arranged in ascending order. Yeah? So the atomic numbers and the periodic table actually arranges the elements in ascending order of their atomic number. Now, it is possible for an element to have the same atomic number but a different mass number. Whenever we have elements having the same atomic number but different mass number, these are known as isotopes. Yeah? For example, if I have carbon, now carbon is a capital C. What is the atomic number for carbon? Hey, boom, is 6. So, 6. Now, the standard carbon is what we call carbon 12, meaning that there are 12 nucleons in the nucleus. Yeah? But there's also a different type of carbon. There's carbon 14, yeah, which is actually radioactive. And these, because their atomic numbers are the same, both of them are 6, which means that it's, it is carbon. But their mass numbers are different. One is 12, one is 14. Well, what would make their mass number different? What's in the nucleus again? Protons and neutrons. So if there are 6 protons here and the total nuclear number is 12, it means that the number of neutrons in this case is 6. However, down here, if the atomic number is 6 and the mass number is 14, then the neutron number here is 8. So isotopes have different number of neutrons. Cool? Nice. And right, so let's move on. Radioactivity. I tell you, we had to blaze through it because we don't have much to do, right? We don't have much time to do all. Now, radioactivity is the process by which unstable nuclei emits radiation or energy, right? Or emits energy in the form of radiation in an attempt to become stable. Yeah? Radioactivity is a random process, which means we cannot predict when it's going to happen. You may have a radioactive substance here, and they're going to say, okay, well, now 50 atoms going on decay. No, you can't do that because it's a random process. And it's spontaneous. So it means that you cannot affect the rate at which it occurs. If you heat it, cool it, do anything to it, you cannot change how much will decay in any given time frame. So what we have to understand about radioactivity is the process of an unstable nucleus trying to become more stable. Everything wants to be more stable. Even us as human beings, we want to be more stable. That's why you all are studying and beating your head against physics, because you all want to get a good job so that you all will become financially stable. Or maybe some of you all were forced to do it. But that's all right. You're still going to do well, right? Don't worry about it. So everything wants to tend towards stability, including atoms. So if an atom can do something to become more stable, it will do it. So unstable nuclei. Instability when it comes to the nucleus can happen because of two things. All right, so instability can occur because the nucleus, either because the nucleus is too heavy, the nucleus has too much energy, or the ratio of protons to neutrons is too off. Yeah? It's just not working for them. Yeah? Now, there's actually one of the very few recognized or globally recognized female scientists that would have contributed heavily as it came to radioactivity. And her name is Marie Curie. Yeah? She would have contributed significantly to a lot of the discoveries when it came to radioactivity. Yeah? So she would have discovered it. She would have discovered various compounds that actually are radioactive, like polonium, and radium. She discovered these, and she would have worked in looking at using X-rays to determine bone structure and all of that. She was really much involved. Unfortunately, she died because of her work. Yeah? She died from radioactive poisoning, because the thing is, radioactive chemicals are poisonous to human beings. We are not supposed to be exposed significantly to radioactive chemicals. So that's why if anybody has been exposed to radiation, you realize that they're taken in to this chamber and they'll actually observe to see what's going to happen to their bodies. You know, from the movies you've watched and these various series you've watched, when radioactive emissions have occurred and they have to be quarantined because they're not sure what's going to happen. She was actually exposed to it and she actually died from it. But she did give us a lot of information when it came to radioactivity. And one of the things that she realized that it was really spontaneous and random. Now, when it comes to radiation, there are three types that we have to look at. There is the alpha particle radiation, the beta particle radiation, and the gamma ray radiation. And if we were to compare these, yeah, now, alpha and beta are particles. Gamma is a ray or a wave. So, alpha particle is a chemical species, right? So it's basically a helium nucleus. If you know what a helium atom is, let's see if we go back to it. Do you see helium? He, He, boom, He. Yeah? So alpha particles are basically helium nuclei. So we know, wow, sorry, my handwriting is just so bad today. We know helium is He. Ha. Now, the atomic number was 2. If you didn't know, the mass number is 4. Now, it's the nucleus alone. So, if it's the nucleus alone, would there be any electrons? No, because the electrons don't exist in the nucleus. Well, it means that there are 2 protons, no electrons to cancel out their charge. So what is the relative charge here? Well, it will be 2 protons, 2 plus. And that's exactly what's going on there. There are 2 protons, no electrons, so the charge is 2 plus. Next. So alpha particles are helium nuclei. Beta particles are electrons. Yeah? So it's not a proton, but its charge is going to be minus. Yeah? Or 1 minus. And gamma particle is a photon or that carries energy in the form of electromagnetic waves. So gamma particles are waves. Now, helium alpha particles are positive. Beta particles at this level, we're going to focus at this level, are considered negative. No, they spoke about positrons here, right? We're not going to speak about positrons right now. But just understand this. Beta particles, we consider those to be the negative ones. And gammas are neutral, have no charge. The atomic number for alpha particles is 2. Yeah? The atomic number for beta particles is sometimes considered to be 1, but we don't really consider it anyway. And the atomic number, pause. Let me rephrase what I was saying. So, it says that the atomic number of the element is reduced by 2 when the particle is released. So, let's look at alpha particle. Alpha is the first letter of the Greek alphabet. That's why we use it. So, alpha is really first. Cool? So, the alpha particle, so let's say that the element before was this value. So, it was sorry, my apologies. It was ZA, right? When the alpha particle is released, yeah, the atomic number goes down by 2. So it means that we'll have to take away 2 from that side. And the mass number will go down by 4. Now, when it comes to the equations, one of the things that you must remember is that the sum of the atomic numbers on both sides must be the same, right? For the equation to be balanced. So if we realize it here, watch. It will be A, boom, bop, boom. It will be A, change the arrow sign to an equal sign, A minus 4 plus 4. Which is it balanced? Because these will cancel out. Boom, A equals A. So we know that's right, right? What about below here? That will be Z is equal to whatever this is supposed to be plus 2. So that means that this will be Z minus 2, and then that will cancel out. So that's why we have that. When it comes to beta particles, however, is different. Because the atomic number is going to go, instead of going down, as in the alpha particle case, the atomic number, when beta particles are released, actually goes up. So if I start again with A, Z, and A, and I put X here instead, and I give off an alpha particle, a beta particle, then an electron has no mass, it doesn't have a nucleus, right? So it means that this must remain the same, because A plus 0 is A. And now, something take away 1 is Z. Well, if something take away 1 was 3, what would the something be? 4, right? If something take away 1 was 9, what would the something be? 10. Because you know to get by the original number, just have to add back 1, right? Similarly, if something take away 1 was Z, then the number would have been 1 more. And that's what you have to remember. So with alpha particles, 2 protons are taken out and 2 neutrons are taken out. But the beta particles actually form a proton in the new element. Now, gamma is a wave. Wave is not is not really made up of particles. Waves are not really made up of particles. So the gamma, when gamma ray is emitted, the atomic structure doesn't change. All that actually happens is that energy leaves the atom. Let's continue. So the emission here changed the chemical element. Now, remember, what defines the chemical element? The chemical element is defined by the proton number. So because here the proton number was changed, or the atomic number was changed, and because here the atomic number was changed, and here the atomic number was not changed, the chemical for alpha and beta, the chemical is going to change. But when it comes to gamma, the actual chemical element is going to remain the same. Now, alpha particles are 2+ ions. Yeah? Which means that they are positively charged. And because they are so much positively charged, it means that they are going to interact with their environment a lot. They are going to pull electrons from here and there and here and there. Think of the size of this value as their level of popularity. The greater that number is, the more popular they are. Yeah? So this is 2+, this is 1-, and then gamma was actually 0. Yeah? Which one is the most popular one then? Well, the helium, because that's 2+. Then the next popular one will be the electron, because that's a 1-. You know, the plus and the minus don't really change. It only changes who it attracts. And then gamma being the least with 0. So, when we speak about ionizing power, let's go here first. Ionizing power is the ability that the atom will have to create ions as it moves. Yeah? So because this thing is so popular and is positively charged, it's going to attract electrons from neighboring particles to come to it and then cause there to be positive ions as a result. Yeah? So alpha particles are the most ionizing. Then we have beta particles that ionize but is not as good as alpha particles. And then we have gamma rays, which are least ionizing because, let's face it, they have no charge, they're not attracting anything per se. Now, that affects their penetrating power. Because if you have to be fighting through and moving through crowds because you're so popular, you're not going to get very far. Yeah? So, alpha particles actually do not travel very far. They are actually stopped by a couple centimeters of air. Yeah? A sheet of paper could stop alpha particles. Beta particles, because they don't ionize as quickly as alpha does, they don't lose their energy as quickly, they actually travel a further distance. So you would need a couple millimeters of aluminum to be able to stop it and to actually work it through. But when it comes to gamma, and because gamma don't really care about anybody and nobody ain't really care about gamma, gamma does just shoot through. Which is why to stop gamma, not even to stop it, but to reduce gamma to tolerable levels, you have to use lead. And a couple of centimeters of lead. Yeah? Some people say about 2 inches, some people say about 10 centimeters. You need to have a good bit of lead to be able to stop gamma radiation from powerful or harmful gamma radiation rays from being emitted or being uncontained. Now let's talk about the speed, because the speed also affects it. Alpha particles are heavy, they're big, they're heavy, and they're already so attractive. They're not going to move very fast. Yeah? So alpha particles move only about 1/10 of the speed of light. So they move pretty slow. Now, I'm saying pretty slow, but 1/10 of the speed of light is faster than any of us can move, right? Well, however, beta particles or electrons move at about 90% of the speed of light. So alpha is only at 10, beta is 90%. And gamma rays, because they are electromagnetic waves, move at the speed of light. That's one of the characteristics for gamma rays. And the last thing I want to talk about is how they behave in electric and magnetic fields. Because alpha and beta particles are charged, they will react with electric and magnetic fields. However, since gamma rays are not charged, they will not react with electric or magnetic fields. So what we want to look at, especially going forward and in our next class, we want to begin to look at the actual relationships, look at actual examples of these types of radiation, and to also look at half-life. Because again, we just have to try and get through the basics and then practice some of the questions so that you will be able to answer some of the things going forward. Have a wonderful one. See you next time.